Hello everyone, I'm Polo from University of Alberta. I'm currently a PhD student. Today, I'm going to be presenting the research work about the transformer-based multi-resolution fast 3D reconstruction for structural damage detection. Actually, it's a collaboration work with Taosun from McGill University and my colleagues Xiao, Dr. Nima Shirzad, and my supervisor, Dr. Qipei. Here's the content I'm going to be covering in this presentation. First is the introduction, and then we'll go through the methodology, 3 phases of methodologies, and then experiments and results, conclusions, references, acknowledgements, and contacts. To begin with, let's take a look at why this research is important. As we know, regular inspections and timely repairs are essential for maintaining the civil infrastructure safety. But as you can see here from the GIF, the collapse of the Nanfang Bridge highlights the severe consequences of structural failure, which often begins with undetected or poorly documented damages. And also detection and the localization of damage within a 3D model is of significant importance because it can provide the engineers a more intuitive or more actionable way to maintain and plan the maintenance. However, current researchers have several gaps. The first one is we have challenges in consistently identifying and matching the same damage across sequential image frames. And the second is that when processing large volumes of images, the normal reconstruction pipeline is usually very time-consuming. So here, our objectives are very clear. First, to enable seamless and efficient maps of surface damage on the bridge onto a 3D model, and then offer decision makers an intuitive and a comprehensive localization of structure assessment. Here's our solution. The proposed framework consists of 3 main phases. Phase 1 is the 3D reconstruction. So we first use drones to fly to get the video data, and then the video data is processed into sequential image frames. And then we use structure for motion to get the sparse point cloud and the associated feature images. For the phase 2, we shifted our focus to the transformer-based damage segmentation. So in this phase, we customized the Swin a transformer model, Swin UNETR. It can analyze and extract the features and provide high-quality defect masks. And then using the you can see my mouse, right? Yeah, using the sparse point cloud from the first phase and the defect masks from the second phase, we can generate the depth maps for the phase 3 multi-resolution dense reconstruction. In this phase, we employ a custom allocation strategy. Actually, we use high resolution only for the defected areas, while low resolution for elsewhere. So the output is a dense point cloud with damage localization and visualization. So here's the more detailed technical details here. For the first part, 3D reconstruction, you can see here from the formula, we need to transform a 3D point in the local coordinate system to the global coordinate system through rotation and translation matrix. So this one is done in the OpenMVG pipeline. So for the second part, transformer-based damage segmentation. So you can see the architecture on the right side of the customized Swin UNETR. It usually, you can see my mouse. It starts by partitioning the input images through different patches and then passes them through different Swin transformer blocks, the hierarchical blocks. Those blocks can efficiently extract both local and global features, and within its shifted windows for using the self-attention mechanism. So for the decoder part, we use skipped connections and the deconvolution to gradually restore the full resolution of the full images, and then finally output the damaged segmentation masks. So for the third part, the multi-resolution dense reconstruction, this one is developed in the OpenMVS pipeline. So the core idea here is that we use the structural components as reconstructed at reduced resolution, while the defect regions identified by the Swin UNETR model are preserved and processed at full resolution. To validate our proposed method, we conducted a few tests on the high-level bridge of Edmonton in Alberta. It's a bridge around 100 years old, and it serves both for the train and vehicle traffics, which makes it a perfect candidate for testing the real-world structural inspection and the complex environment. So we use the DJI-3 Pro. We use the DJI-3 Pro drone to collect video data by flying around the PS structure and collect the video data. And then the video data, we extract the sequential image frames at a rate of 1 image per second for the further processing. And then we use structure for motion to get the sparse point cloud with the camera poses. You can see here, this is the camera trajectory. And for the segmentation model training, we used the public dataset, crack dataset, which consists of around 6,000 crack images. And you can see the loss is decreasing steadily after 300 epochs. And the validation dice coefficient is increasing and steadily, yeah. So that means the Swin UNETR model can learn certain feature to to distinguish the crack on the concrete background without overfitting. So after segmentation, we need to calculate the depth maps. So this depth map is one of the input images. So it will guide the stereo matching process for the dense reconstruction. So the final output is the dense reconstruction point cloud here. It's a point cloud, but with the defect areas highlighted in red with full resolution and fine detail, while the elsewhere, like the pier structure, other components is we reduced by 2 times. It's a low resolution to save resources. So to quantify our performance, we conducted one-time comparison with our method to the normal full resolution, uniform resolution reconstruction. So for example, it shows substantial time savings. For the first line, you can see the depth map estimation. It's reduced from 25 minutes to around 8 minutes, which is reduced by 17 minutes. So overall, the multi-resolution approach reduced the total resolution reconstruction time by around 64% and it decreased the memory consumption while maintaining high quality defects. So to conclude, first, the structure for motion can effectively capture the global geometry of the structure, and the customized Swin UNETR model can accurately segment surface defects. And the computational efficiency is significantly improved by prioritizing high-resolution reconstruction only in damaged areas and reducing detail in non-critical regions. Finally, the experimental results on the high-level bridge demonstrated a 64% reduction in processing time and effective defect localization. For the future directions, first, we want a generability, like expand our method to other defect types like spalling, mold, corrosion, etc. And the second one is the mesh optimization. We can use the same idea like here, like we can use high resolution mesh for only the defected area and the low resolution elsewhere. And the third one is what I'm working on right now is the autonomous drone navigation for structural inspection to save manpower. As you can see here, all you need to do is hit the start button and the rest of the things is take care of the algorithm. So to save manpower, because now we still need a pilot to fly the drone, right? Here are the references we referred to. And yes, we acknowledge the financial support from ISARC and Alberta Innovate. And if you have any questions, you can ask me now or reach out to me through my email address here. And if you want to learn more interesting ongoing projects, please go to our website at maylab.com. Yeah, that's it for today.